use the word secant line here just because it does show up in our textbook sometimes. Really, when we're talking about the secant line, we're really just saying we're looking for the equation of the line passing through 2 points. So for any equation of a line, there's always 2 things I need. I need a slope and I need a point. So in this case, in order to find the slope, I kind of first have to figure out the points. I'm going to do that by looking at the 2 x values that we've been given. And if I'm at an x value of 1 and I head up to the graph, then the y value there I'm going to get from the function itself. I mean, I'm going to plug in 1 for x, the square root of 1 is 1, and there we go. For my second x value of 4, if I head up to the graph, I look at the function says take the square root of the x value, the square root of 4 is 2, and that puts me at a y value of 2 over there. That means that in terms of that equation of a secant line, I really could use either of these points. It doesn't matter which one, I'm going to go ahead and choose to use 4, 2 as my point. Generic equation of a line, I'm going to write as y minus y1 is equal to the slope times x minus x1. And I'm going to go ahead and substitute that point in right now. Always thinking about partial credit, looking to do the easy stuff first. So I'm going to plug in the 2, plug in the 4. The next step for any equation of a line is I've got to figure out what the slope is. Here, because I've got 2 points, I'm going to get my slope by looking at the change in y over the change in x. Doesn't matter which order you do these in, it just matters that we keep the order the same. So I'm going to write this as 2 minus 1 in terms of the difference of the 2 y values over 4 minus 1, the difference in the 2 x values. That's going to leave me with 1/3. So my equation for the secant line I could write as y minus 2 is equal to 1/3 of x minus 4. Now it's totally fine to leave the equation of the line this way. If it is bothering you that it is not looking like y equals mx plus b, we can do a little bit of rearranging to get there. But I'm going to go ahead and leave it alone. I'm going to pause there for a second in case there are questions about that. Great, I'm going to move on. Okay, I mentioned that today's topic was going to be derivatives. The whole big picture idea of what's happening with derivatives is to say, well, wouldn't it be cool if instead of having to find the equation of the line between 2 points, what if I was really actually interested in what was happening really, really near x equals 4? So close to x equals 4 that I actually want to be able to find the slope at a single point. And we're going to do this using our new tool of limits. I'm going to go ahead and redraw my graph just so that it doesn't get too messy on me. And so here's my graph. I'm looking at the same function. This time I'm going to give it function notation, and I'm going to call it f of x is equal to the square root of x. And I'm kind of going to come back here to that x equals 4 value. Well, if instead of trying to find the secant line, meaning the line between 2 points, I wanted to find the equation of the line exactly at 4. We have a different name for this line. We call this the tangent line. And really, we're imagining if we were able to zoom way in on that point, if we got close enough, this graph really right near that point would look like a straight line. And so what would the equation of that straight line, or what would the slope of that straight line be? And I'm going to do my best to draw it in here. So really, that's the thing that I want to get to. But I'm going to creep up on it. And here's how I'm going to creep up on it. I'm going to say, okay, well, I know that if I found the equation of the line between 1 and 4, between x equals 1 and x equals 4, it's not exactly this line. It's got a slightly different slope. But what if I just moved over a tiny bit? How small? Like a hair. And hair starts with h. So I'm going to scoot just a hair away from that 4. And I'm going to call that distance h, because it's just a hair away. And that means that if this was an x value of 4, then my new x value is 4 plus a hair, or 4 plus h. Now, if I go up to my graph, I know that at 4, that y value would come from me plugging 4 into the function. And the square root of 4 is 2. And at 4 plus h, I would get that y value also by plugging it into the function. It's just, if I plug in 4 plus h, I'm going to end up with the square root of 4 plus h. There's no way for me to simplify that. I know that if I needed to find the equation of the tangent line, I need a point and a slope. And really, I want to investigate what's happening with this slope. And we'll see if I can give myself enough space over here. I think I can. So my slope would come from my change in y, which is looking like the square root of 4 plus h minus 2, it's my other y value, all over 4 plus h minus 4. Now something convenient happens on the bottom here, and that is that my 4 minus 4 is going to cancel out. So really I'm looking at the square root of 4 plus h minus 2 all over h. And if you're looking at that right now and thinking, well, how is that a slope? Because we don't know what h is. Here's where we layer on the calculus fun. If what I'm looking for is the slope at exactly 4, then what I'm trying to do is squeeze these 2 points until they're basically the same point. And if I'm squeezing these 2 points in together until they're basically the same point, that means I'm letting the value of h go to 0. And we know how to deal with that. We're going to write that as a limit as h approaches 0. Now, all of our same limit rules apply. First thing I'm going to try is to plug in the value. Well, when I plug in 0 for h, I'm going to need a little more space here. When I plug in 0 for h, on top, I'm going to end up with square root of 4 plus 0 minus 2. And on the bottom, I'm going to end up with 0. When we do the arithmetic really quick, 0 plus 4 is 4, square root of 4 is 2, 2 minus 2 is 0, and I got 0 over 0. Just like any of our other limits, when we get 0 over 0, it is telling us to go do some algebra. Since I've got square roots, the type of algebra that I want to do is to multiply by the conjugate. So I am looking at a limit as h approaches 0. And we've got our original piece, the 4 plus h minus 2 all over h. And we're going to multiply that by the conjugate. So I'm going to have the square root of 4 plus h plus 2 over the square root of 4 plus h plus 2. Our whole objective is to get rid of that 0 on the bottom, which means my hope is that we're going to be able to get rid of that h. In order to do that, I do not want to distribute the bottom out, because if I do, it's going to be counterproductive to me trying to solve for h. But I do want to distribute the top out. And that's where I'm hoping an h is magically going to appear for us. Well, on the top, the square root of 4 plus h times the square root of 4 plus h gives me a 4 plus h. The whole reason that we've multiplied by the conjugate is so that those middle terms will cancel out. I'm going to write it out once, but moving forward, we just want to remember this happens every time we multiply by the conjugate, which is the whole point of doing it. If I'm kind of foiling this out, so I've got square root of 4 plus h times square root of 4 plus h. That's what gave me the 4 plus h. I'll have a positive 2 times the square root of 4 plus h. And then a negative 2 times the square root of 4 plus h. And then negative 2 times positive 2 is going to give me a negative 4. And on the bottom, I'm just going to leave this as h times, and then we'll leave the rest of this in parentheses. Square root of 4 plus h plus 2. Well, on the top, conveniently, I know that our conjugate pair pieces cancel out because I've got the positive of it and the negative of it. I've got this 4 and the negative 4. So those are also going to cancel out for me. And now the only thing we have left on top is h. And conveniently, h over h is equal to 1. So now, after all of that, I still haven't taken the limit, but I'm about to. So on the numerator, I've got a 1, and in the denominator, I've got the square root of 4 plus h plus 2. And if I plug in the 0 for h at this point, nothing bad happens. 4 plus 0 is 4, square root of 4 is 2, and I am looking at 1 over 2 plus 2, or 1/4. This technique is really the definition of finding the slope at a single point. It's our definition for finding the slope of a tangent line. Now we happen to do this at a particular value of x, at the value of 4. But we could write this even more generically. And if I redraw my picture to give it an even more generic spin, if I just called this point x, and then I moved over just a hair to be at x plus h, and this I just called our function f of x to get the y value at this point, that would be f of x. And to get the y value at x plus h, that would look like f of x plus h. So when we talk about the definition of the slope at a point, we're really using this most generic form to say we would get our slope by doing the change in y values, or f of x plus h minus f of x, it's my change in y's, over my change in x values. Now, every single time, no matter what the x value is, I know that the difference between them is always h. It's that tiny little hair that we've moved over. And to actually get the true slope at the point, we're going to want to take that limit as h approaches 0. And this right here is how we define the derivative. And there's a bunch of different notation that we can use, but one of the most common pieces of notation is to write this. It looks like f apostrophe x, but we read this as f prime. We actually have two choices for how to approach this. Anytime we're looking for the slope at a particular point, we can go ahead and plug that x value in to our limit definition of the derivative from the beginning. Alternately, we can use the limit definition of the derivative generically, dragging that x along with us, and then plug in the x value at the end. There are advantages to both. Because this is our first example that or our second example that we're doing, I'm going to go ahead and use the most generic form, and then we'll go ahead and plug the x value in at the end. So if I dive into our limit definition of the derivative, and this is something that you'll probably be expected to memorize, I'm looking at the limit as h approaches 0 of f of x plus h minus f of x all over h. If there is a place where you're likely to make a mistake on this, it's right here in the step where we're plugging in x plus h. So I want to make sure to pay special attention to that up front. Whenever you're in doubt, try plugging in numbers to get a sense of what's happening in the problem. So if I think about, here's my function. If I wanted to know what f of -3 was, that's going to tell me to plug in -3 everywhere that I've got an x. If I wanted to know what f of 172 was, I'm going to plug in 172 everywhere that I see an x, which means when I need to know what f of x plus h is, I'm plugging it in kind of in parentheses everywhere that we have an x in the function. We don't actually have to do this in order to do the problem. This is just me kind of helping us to see what that notation means. So let's dive in. And since I've already written out what f of x plus h is going to look like for us, I'm just going to copy it down again. So that f of x plus h piece, think of this as a formula. We had to come up with what f of x plus h is in order to plug it into the formula. This is what f of x plus h is. I am looking at x plus h squared minus 3 times the quantity x plus h. The next part of this formula is that I have to subtract off f of x. I like to go ahead and put that in parentheses just to make sure that my minus sign is definitely going to get distributed through. X squared minus 3x. And then this whole thing is all over h. Now, I'm going to pause for a second just to acknowledge that I know some of you have taken calculus in a previous life. And so if you're pretty sure that you already know what the answer to this derivative is going to be, go ahead and put the answer you think in the chat. And I have the chat set so that only I'm going to see it. It's not going to go to anyone else. I've got a couple guesses coming through. If you don't know, that's okay. We can all be surprised together by the limit. I just got 2 guesses in the chat. Okay, that probably means that we should do the limit together to make sure that we can all get there. So if I look at the numerator, oh, I don't want to skip this step. First thing we try with the limit problem is to plug the number in. I'll do the easy one. We're definitely going to get 0 in the denominator. If I plug the 0 in on top, essentially those h's should go away, which means I should get 0 on the top also. When we get 0 over 0, we have to go do some algebra. In this case, the algebra that we're going to have to do is to multiply everything out and hope some stuff cancels. X plus h squared, that's the same thing as having x plus h times another x plus h in parentheses. So when I multiply that out, I'll get x plus h plus 2 of the x times h terms plus an h squared. On my next piece here, I'm going to distribute that -3 through. I'll have -3x minus 3h. Here I've got a minus sign to distribute through. I've got minus x squared minus a minus will make that a plus 3x. If we have done everything correctly, then in the numerator, all of the pieces that don't have an h should cancel out for us because we're hoping that in the end, this h on the bottom cancels out. So let's see. My positive x squared has a negative x squared counterpart, so those can cancel out. 2xh doesn't have a friend, so we're going to leave it alone. H squared doesn't have a friend, so we'll leave it alone. My -3x has a positive 3x counterpart. And my -3h does not have a friend. So everything that's left has an h in it, meaning I can choose to either break this apart into 3 separate fractions, or I can factor the h out. Both totally work. Sometimes the breaking apart into the fractions is helpful. I'm going to go for, yeah, why not? I'll break it into fractions. So I'm going to have 2xh over h plus h squared over h minus 3h over h. Now I'm almost ready to take that limit, but I might as well simplify my life one more step, meaning this h over h is equal to 1, and this h over h is equal to 1, and that h squared over h, well, I can get rid of one of the h's on top, so that I'm looking at a limit as h approaches 0 of 2x plus an h minus a 3. And if I plug in 0 for h, I'm going to get 2x minus 3. Really what that 2x minus 3 is telling me is that's the rule for how to get the slope at any point that I might be on this graph of x squared minus 3x. So that's my rule for how to get the slope. So if I care about the slope at x equals 2, one way that we might write that, just using notation, is to say we're looking for f prime evaluated at 2. That 2x minus 3, that is our f prime, or the derivative. And when I evaluate it at x equals 2, I'll end up with 2, oops, not times 3. Evaluating it at x equals 2. 2 times 2 minus 3, which is going to give me a slope of 1, which is what a couple of people gave me in the chat earlier. So again, when we go through this process and find the derivative, that derivative is telling us the rule for how to get the slope at any given point. And the nice thing about doing it kind of generically from the beginning is that now I could find the slope at any point. So if I wanted to find the slope at x equals 0, then I just have to plug in 0 to our rule. There we go. I'd get 0 minus 3, negative 3. And I could do this for any point. So if I'm going to use the limit definition to find f prime of x, that means I'm looking for the limit as h approaches 0 of f of x plus h minus f of x all over h. I don't have a lot of space, so I'm not going to write that limit definition out. I'm just going to go ahead and apply it to the function. Well, f of x plus h says wherever there's an x, plug in instead x plus h. I'll end up with 5 times x plus h cubed plus 1. And then we're subtracting off from that our function. So 5x cubed plus 1. And that whole thing is over h. First thing we try with a limit problem is plug in the 0. If you've done this correctly, you should always get 0 over 0. So I actually skipped that step. Since we got 0 over 0, we're going to have to do the work multiplying that top out. And that's going to be a little bit gross because I gave us a cubic. I don't know whether you all have seen this. I hope you've seen this somewhere in a previous life. But there's kind of a shortcut for multiplying out what we call a binomial term raised to a power. And we can do this, we can get the coefficients from Pascal's triangle. So if you haven't seen this before, it is kind of a neat trick. It's a neat shortcut. The way Pascal's triangle works is we keep adding ones to the outside, and to get the values on the inside, we add terms kind of like down in a funnel. So to get that third row, I'd have ones on the outside, and 1 plus 1 would give me a 2. To get that next row, I'd have ones on the outside. 1 plus 2 is 3. 2 plus 1 is also 3, and I'd have a 1 on the outside. And you can keep going and keep doing this. 3 plus 1 is 4. 3 plus 3 is 6. 3 plus 1 is 4, and I'd have a 1 on the outside. And we can continue this pattern. What this tells me is the coefficient of the terms when I multiply everything out. So if I look at this row right here, the 1, 2, 1, and I go back to our previous problem, when we multiply out x plus h squared, the coefficients are 1, 2, 1. Since we're multiplying out x plus h cubed, I'm going to need this line right here. And I know that my coefficients are going to look like 1, 3, 3, 1. Now to get the terms themselves, I'm going to look at the x and the h, and I'm going to start by taking the x to whatever the power is that we're raising the whole term to. So I'm going to grab that coefficient of 1, and I'll have 1. Oh, sorry, I don't want to lose my 5. I'm going to keep my 5 out in front. So now I'm just looking at the x plus h cubed part. I'm going to have x, I'm going to have 1 from the coefficient times x to the third. And then I'm going to decrease the power on x each time and increase the power on h. So my next coefficient is a 3. I'm going to decrease the power on x. So now that's x squared. And there was secretly an h to the 0 here, meaning when I increase the power on h, it would be h to the 1. Next, I'm going to take that coefficient of 3, decrease my power on x. So now I'm on x to the 1. And increase my power on h. So now I'm at h squared. Next up, I'm going to have that coefficient of 1. And that coefficient of 1 is going to be 1. My x power goes down to 0, and my h power goes up to 3, and I'm done. Now, I don't know if I left myself enough room here, but I'm going to try to squeeze it in. Still going on the top, I've got a plus 1. And then distributing that minus sign, I've got minus 5x cubed minus a 1. And I will just draw a little bubble around Pascal's triangle. Keep it out of my way. And that whole thing is over h. Good times. Next up, I'm going to distribute my 5 through. But I am going to go ahead, I can already see that that 1 and negative 1 are going to cancel. So I'm going to go ahead and do that. And I can already see that when I distribute the 5 into the x cubed, that's going to cancel out with that negative 5x cubed back there. So I'm going to skip writing that. And I'm going to go straight to distributing my 5 to the rest of it. So 5 times 3x squared h leaves me with 15x squared h. 5 times 3x h squared. 15x h squared, and 5 times h cubed is just 5 times h cubed, all over h. Now the request this time was to show factoring out the h instead of breaking it up as separate fractions. So I'm going to go ahead, and on the top, I've got an h in every term. So if I pull that h out, I'm looking at 15x squared plus 15x h, because I only pulled out one of the h's, plus 5h squared, again, because I only pulled out one of the h's. And that whole thing over h means these guys cancel out, and I'm ready to plug in my limit of 0 for h. I'm going to have a 15x squared, and when I plug in 0 for h, this term goes away, and so does this one. And that is my f prime using the limit definition of the derivative.